And here we are in the lab again, and welcome to episode 16. So, in the last video, we configured the PMP, the parallel main port, as they call it. And so we were able to send data out through, out of the PMP and through the bus transceiver to the SRAM. And we verified that with the scope. So now in this video, we're going to go to the next level, and we're going to write to a memory location with MainBrain, and then we're going to read it with the I/O board, and we're going to display that data on the LED port, the LED display. And then once we do that, then we're going to reverse the process, and we're going to take the I/O board and write to a memory location, a different memory location. And then we're going to use MainBrain to read that location, and we'll display the whatever's in that location on MainBrain's display. And that should pretty much wrap up the video. I'm going to try to keep these videos around 30 minutes. I don't know how you guys feel about it, but I like 10-minute videos. But I can't do a 10-minute video on most of this stuff. So I'm going to shoot for 30 minutes and see what I can do. Keep it as simple as possible and short as possible, but still have a lot of content and stuff. So we'll see. It changes over time. Everything changes over time. So we'll see how it works out. So that should keep us busy for 30 minutes. So let's get to it. So there's some new stuff since the last video. They have this new compiler out for the DSC microcontrollers. So if you come over here and right click and go to properties, this is where you select your compiler. So the XC16 is what we were using before. So now we have the new DSC, and they've already updated just a little bit of a bump on their version. So then so I updated that part in the header thing there, and I added my comments. I like the comments on top. I don't like them over here on the end after it. I mean, it's up to you. So I added some more comments, and then I added the control lines for the SRAM. So we have the chip enable for it, the busy signal. When there's two writes at the same time, then this busy signal goes low. And then they have a semaphore pin. We're not using that. You can use semaphores to keep from writing at the same time, but I never got it to work satisfactory. So what I have implemented now is, we'll get into later, is kind of what works best so far, and that's using the busy signal. And so Mint, the memory interrupt, that's another subject for later, but you can generate interrupts both directions through the SRAM by writing to certain parts of memory. So we can get into that later too. So this is our, just for the prototype board, where we have to flip that, our buffer, our bidirectional transceiver buffer, where we have to flip that around in the next revision, and this takes care of that. It's a workaround for that, just temporarily for this prototype only. So then we have the read-write signal. Now the read-write is actually being generated by the microcontroller, the PMP. So we might can take that out. So then, oh, and now is what we're doing here. I commented out the heartbeat, and I commented out turning LED 7 on. So that leaves the LED port completely open for us to write to. So this is the chip enable RD14. So we're gonna, that's normally low, or I mean, that's normally high. So we're gonna pull it low, and that enables the SRAM. And then we're gonna read what's in the SRAM at the preset memory location, which is 0 right here for the moment. And it's gonna read that. So the variable is, it's gonna read it and put it in this variable A here. And now this is just, you don't want to do more operations until it's completed doing its thing here. So you just put this in while it's busy, then you just wait. You wait for it to complete, and then once it's completed, then you deactivate the chip enable. So that releases the SRAM to do whatever. It may it another board could then access it. So then you take A and you write it to the port and display it to the port using our function we made earlier. So basically it's a continuous loop. That's our main program loop. And it's just looping through this, reading it and reading it and reading it over and over again and putting it onto the LED port. So that means anytime that memory location's data changes, it will update it on the LED port. Okay? So then that's pretty much all that I've added in there. So then let's load up the MainBrain project, because MainBrain is writing to this 0 location in SRAM. And so there we go. So we load that up. So we got our MainBrain in there. So now if you look, see, we have the IO board is using the DSC compiler, but MainBrain uses the XC32. And you can do that at the same time. We've made IO board the main project. So when you hit this program button, it programs the IO board. And so when you want to update another project, then you can either set it as the main project and hit the download button, or you can just do it manually right here, make and program device. But you either have to move your PIC kit to a different board physically, or you can have one, you can plug one in and it will show up here and you can select it. And you can actually run 2 PIC kits at the same time. And the PIC kit 4s and 5s do that really well. PIC kits 3, maybe not so much. So it's what I did on MainBrain. So MainBrain, whoops. So our source file, MainBrain has a lot of source files. We're going to add more source files to our IO board. So each little different module, I use a different file, different C file, source file. So what I'm doing here, so let's load up, let's see, the main source file. And so down here, as you come down, we do a lot of, it's basically the same as IO board, it just has a lot more stuff to do. So coming down here now, So here's the test I/O board. So we're doing just a test, and we're writing to this location, memory location 0, and we're writing the value, hexadecimal value C0 to it. And just one time. We just do it before, at the end of all our initialization, we just send that out there and write to the SRAM. And that's the only thing that MainBrain does right now in relation to our I/O board. So we can change this, and maybe we'll do that. So if we go and look at our board, we'll see that the LED port does show the binary value C0. Okay, so as you see on the board, I got my dry eraser right here as to cause a shadow, just a little bit of a shadow over the LEDs so you guys can see it better, because without a shadow, the camera doesn't pick them up good enough that you guys can distinguish whether it's on or off sometimes. So especially like it gets a glare down here on the lower bits. So that shadow, it looks pretty bright, but they're really not. I mean, they're bright, but my eyes do not see what this camera sees. So anyway, that's just so you guys can see it better, so you know what I'm talking about. So you can see that the LEDs represent the data. Well, at least this shows the data being shown on the LEDs is a binary representation of the SRAM, which is hexadecimal C0. And so in binary, that's 1, 1. Using the green LED as our most significant bit. It's 1, 1, 0, 0, and then 0, 0, 0, 0. And that's hexadecimal C0. So then we'll jump back to the code and we'll change the value in MainBrain, and it should change out here. And then I'm going to discuss, I have to make one change to our design, and I'll show you why I have to do that and what it is. Okay, so let's go over to MainBrain's main C program, and where we write CO to the memory, we're going to change that to say, let's do like 96 hex. And you got to pay attention, because sometimes you write 96 decimal and then you expect a 96 hexadecimal, and you go, what happened? Why is it not working? And then you look and you didn't do the right base for your number. But anyway, so we're going to write 96 to it. So I'm just going to go and set this as the main program project. It makes it a little easier. And then all you have to do is just come up here and we'll send it to MainBrain. I already have the PIC kit hooked up to MainBrain. So it takes a little bit longer to program MainBrain because it's a bigger file. But it's not too bad considering. All right, there we go. So then if we go look at our board, and we will see that our LED port does reflect that change. So that is conclusive proof that we can transfer data across the SRAM, across the data cable, through our buffers, using the PMP port of the microcontroller to our LED port. So I mean, that's what we want. So then we're transferring data from MainBrain to the microcontroller. So then let's transfer data from the microcontroller back to MainBrain and see if we can do that. So we'll come over here to MainBrain's main source file, main function. So we're going to do pretty much the same thing right here that we did on the I/O board to where it runs the loop, its main loop, and it just reads from the SRAM and will display that on the screen. So that's a little bit different because we have a display that we can display something on. So normally, MainBrain displays the home screen. So we're just going to hijack a section of the home screen, and we'll just put it right up here and override, and just blast our number right onto the screen. So we're going to read a different memory location than we're writing to. So we're going to read location 1, and we'll make this the read command. That's our a memory read function, and we're going to read memory location 1. We'll just make that 01, simplicity's sakes. All right, so we read 01. So then in my functions for the SRAM, we have the read. So when you read, you input, it takes an integer, a 32-bit integer address, and it reads it and spits it out on this variable, a global variable here. So there's 2 ways that you can do it. You can create an integer and just say that integer equals, read that, or you can just use the global variable called mdata underscore 70v05 to distinguish that SRAM from any other memory location, because we have internal flash and data, and we have external flash and external SRAM. So we have to distinguish between all those sections of memory, all those memory devices. So then we want, so mdata is where our memory data is placed after we read this, okay? So we're going to just make a note of that right now. And then we're going to do an operation. We want to display that. So in order to display it, we have to convert it from the binary value to either a BCD representation or a hexadecimal representation. So we're messing with hex right now, so we'll use this hexadecimal representation. So we'll click on this. For some reason, there it goes. And so this what it does. It takes your integer, which will be the memory data, and it converts it into a hexadecimal representation, an ASCII representation of the hexadecimal value. So and just to make it short, it converts it into something that we can display. So it's going to display like for 95 hex, you input that in, it spits out two characters, a 9 and a 5 on the display. All right. So all you have to do is take this guy right here, go back to our main. So we're going to convert it. We're going to convert mdata. So mdata gets put in here. So when you do that, then you have some global variables over here called dhex 0 through 7. So depending on how big, you can go convert up to 32-bit, a 32-bit binary number. But we only have an 8-bit number we're plugging in. So we'll come over here. And so binary to ASCII hex, and then our binary value, and then that spits out the data into our global variables. Oops, I did not want to do that, did I? So we got a copy. And so we should be done with that. And so then once it converts it, then we have our variables. Since it's just 8-bit, it's 2 characters, so that's 0 and 1. All right. Okay, so D hex 1 is the most significant number, and 0 is the next least significant number of this. So on the display should show 96. Well, whatever we find in here, it will display it on the screen. So then we have to call the screen function to actually display it. We don't need that. And so display function. So there's a lot of display functions. So down here at the bottom is we want to write a character, which is right character right here. So we take this function, all right, so we put it right here. We want to put it on the display. So we write character. So then we want to the start column number, and I usually just indent it like 10 pixels. And then the unsigned row, we want to bring it down, say like to 30. And then the ASCII character, which is, we want to do the most significant one first. So that goes in here. And then our text color, we want black, which is, I already have black defined in there in my header file. And then the canvas color, the background is going to be white. Okay. And with the semicolon. And then that writes the one character, then we got to write another character, the next one. So we're going to copy that, if I can do it right. And see, MainBrain is at a lot higher level now, because it has all these functions that I've written before over the years to take care and handle different things we want to do. And it makes it a lot easier than like coding everything on the device level. So we make that a 0. So that's our 2 characters. So this one we want to add, let's see. So our column is 10. So we want to add about 15. So then that will be 25. Okay. And then 30 stays the same to keep them on the same line vertically. All right. So then that should do that first thing when it starts its main program loop. So I think that's all we need to do there. Let's send it over to MainBrain and see what happens. So you see our number popped up on the screen, a MainBrain, and MainBrain's upside down to you guys. So we're going to flip that around for you too. We can do that. So we have an arbitrary number of 42. So is that a real number? We're going to find out. Okay, so let's flip the screen around on MainBrain for you guys. I could do it in the video, but I just want to show you how you can control the screen, give you a little sneak peek on the screen, because we'll probably get into MainBrain a lot deeper later on too. So on the display, on the initialization code for the display, the MainBrain calls that when it boots up, gets the display configured so it can do something. So right here, I have notes. You should always try to keep as much notes as possible, because as the years go by, you might not remember all the details. So right here, it says connector on the right-hand side, which must be what this is. So we want to go to the opposite, which is the left-hand side, and we just make this an E right here. And then we just compile it. Okay. So as you can see, the screen flipped around for us, and that was a fairly easy thing to do. So we got our 42 in there. So now we're going to jump back over to the code for the I/O board, and we're going to we're going to write to that memory location 1 that we're reading over here on MainBrain, and see if it changes, and see if the values match. Because if the memory, if it doesn't have the wait state, or something's not set up right, or something's backwards or something, then it's not going to be uh, identical numbers on both sides. So that's one thing we have to prove that we can do. So the next thing is to write the code that makes the write cycle to write the data to the SRAM at location 1. So the very first thing we got to do is set the location we want to write to. So we set the address right here. And we're going to set that to the 1. Okay. So then the next thing we want to do is start the cycle with the chip enable, or a chip select, whichever you want to call it. So that's up here. So I'm going to copy the whole thing. We don't need truths, but I'm going to copy the whole thing because I'm being lazy. Like that. And then we're going to take the truths configuration out. So chip enable, I'm going to copy that because we're going to end our cycle. We're going to begin our cycle with a 0 to activate it. And we're going to end our cycle by just deactivating it with a 1. All right, so then the next thing we got to do, we have to tell our bidirectional buffer, our 245 chip, we have to tell it what direction we want, because of our problem we had earlier where we had to just add this in manually. So we're going to grab RE9 here. We're going to paste it in here. And we're going to take the triz out. So 9 is 0, so we're going to hit it with a 1 to change directions, to send data out to the SRAM. But then, of course, we have to end our cycle by bringing it back to a 0. And so then we have to do a write. We have to tell it we want to write to it. And then we're going to grab this, the read write. We're going to plug it in right here. Get rid of the triz. All right, so then we're writing, so it's 1 for read, 0 for write. So we're going to go like that. And then, of course, we're going to end our cycle by bringing it back to 1. So get rid of the triz, get rid of our dead space. All right, so then the only thing left is the main star of the show is the actual command for the PMP to write the data onto the data bus. So if we come over here to our data sheet, then we'll see that PMD out 1 is for dual buffer host mode in the write mode, okay? So we'll copy that, come over to our code, and paste that in there. And then that equals, and we'll call it, how about a 58? But we got to make it hex. Hexadecimal 58. Semicolon. All right, so that is our entire write cycle right there. And after we're done with our write cycle, we set the address to 0, and then we do our reading loop. So that should work. So then send it to MainBrain, or send it to the I/O board. And it looks like it worked. It changed, and we have the value 58, which we told it to write to memory location 1. Okay, so we can actually now send data bidirectionally across the system, from one end to the other, from the microcontroller to MainBrain, and from MainBrain to the microcontroller via the SRAM. So it looks like so far so good. I think I'm going to cut the video right here because I want to keep it at around 30 minutes. I don't want to get too long-winded on them. And so I think that sets us up on the next video to refine. We're going to do, like I said earlier, we got to create some functions to read and write to the SRAM properly, so we don't have any contentions or lost data. And so that's probably a video on itself coming up. So yeah, I will see you in the next video.